So here in number 11, we're asking ourselves, what would happen if we add half a mole into a liter of solution that has 0.5 molar HClO2? So I'm going to start by writing the reaction that's pertinent to the solution we already have. So the solution we already have is this 0.5 molar HClO2. And HClO2 is a weak acid. Oops. So we're going to have the dissociation of HClO2 aqueous into protons and ClO2 minus. So that's the equilibrium we're thinking of. And we're adding this NaClO2 to the solution. So as I've written above, it's going to dissociate into sodium ions and these chloride ions completely. And so the sodium is not going to be involved in our reaction at all, but these chloride ions are involved. So when we add our sodium chloride into solution, we're essentially adding in more of this product. When we add in more of the product, we're going to shift our equilibrium to the left, toward reactants. And so when that shift happens, some of the protons are also going to be pulled to the left. So our proton concentration is going to decrease, not increase. And if we're decreasing proton concentration, we're becoming less acidic, and our pH is going to increase. Okay, then our HClO2 is going to increase because we're shifting toward that side of the reaction. And then now we have to think about hydroxide. Hydroxide's not in our reaction, but we have to remember that Kw is equal to our proton concentration times our hydroxide concentration. And so we already established that we're decreasing our proton concentration. And so that means our hydroxide concentration must be increasing. Okay, so all three of the last ones are true. Okay, so now we have this reaction between acetic acid and KOH. So when I'm trying to figure out what reaction to write, I like to always start with the strong species. So I have the hydroxide from the potassium hydroxide, and I have that weak acid with it. And this is a neutralization reaction, and it's going to completely react until one of our reactants runs out. And so the hydroxide is going to take the proton from the acetic acid to make water, and that's going to leave behind the acetate ion. And so they want us to figure out what species are present in significant amounts after we add some different amounts of our reactants. So when we have a reaction, we're going to need to use an ICF table instead of an ICE table. Whenever you have reaction, ICF, and for our ICF table, we need to always put in moles. A hint that that might be the case is if they give you volumes in addition to concentration. So we can use the liters and multiply it by the molarity to get the moles of each species. So for example, for the acetic acid, we can say we have 0.05 liters times the molarity, which is the same as saying 0.25 moles of the acetic acid present in 1 liter. And that will give us an amount of 0.0125 moles. And then we can do the same process for the KOH, and we're going to add 40 mils of that, which means we have 0.01 moles of the hydroxide. We're going to ignore the water, and they didn't tell us anything about starting with acetate, so we're going to put 0 moles there. Now we're going to look at our reactants and figure out which is our limiting reagent, because that's what we'll run out of first and we'll stop the reaction. So that's going to be the one with the fewer number of moles, and so that's going to be the hydroxide. So we'll use up all of our hydroxide. And we'll have some of the acetic acid left over, and we'll make that much of the acetate ion. Okay, so then we can look at the results of our ICF table to figure out what we have. And one of the things we see is we have our acetic acid present, and we have the acetate ion present. And so we could identify this as a buffer. Okay, doesn't really matter for this question, but it is a buffer. And so we can look at what's left, and we have just these two things present in solution, because we used up all of the hydroxide. It was limiting. So the correct answer here is D. Okay, so here we're figuring out the pH of a solution of aniline, and they give the formula there. They give us a Kb, which is a hint that this is going to undergo base hydrolysis. We also know it's going to be a base because we're going to have some carbon chain attached to nitrogen, which then has 2 hydrogens coming off. It has a lone pair. So here we have a nitrogen with 3 bonds and a lone pair, which makes it a weak base. So whenever we're trying to find the pH of a weak solution, we can put that weak thing in water and go ahead and ice it out. Okay, and so for ice tables, we always put in molarity. So here the volume doesn't actually matter. We're just going to go ahead and use our 0.5 molar. Okay. We only need moles when we have some sort of reaction going on. Okay, we're going to ignore water, and we're not starting with any of that stuff. So we can go ahead and do our change as minus x, 0.5 minus x, plus x, plus x, x. Okay, and then we can go ahead and write our Kb expression. And we have our aqueous products over our aqueous reactants equal to that Kb. We can plug in our equilibrium row to that expression and get x squared divided by 0.5 minus x. Okay, but our Kb is small enough. It's 10 to the minus 5 or smaller. So we can ignore the minus x. So solving for x is pretty easy. We just have to do some multiplication and then take the square root. And we get that x is equal to 1.38 times 10 to the minus 5 molar. So then if we look back up at our ice table, we can see that this is going to be equal to our concentration of hydroxide. So when we go ahead and take the negative log, we'll be solving for POH. And that ends up being 4.86. And so our pH is going to be equal to 14 minus 4.86, which is going to be equal to 9.14. And this makes sense because we started with a solution we knew was a weak base, so we should expect to get a pH greater than 7. So the answer here is A. Okay, so now we're going to try making buffers. And so we know that to have a buffer, we need to have something weak and we need to have its conjugate. And so let's just go through these one by one. And the first one we have HF, which is a weak acid, and we're adding to it NaF. So the NaF we know is going to completely dissociate into Na+. Try that again. Into Na+ and F-. Okay, so as we add these two things together, we have something weak, and we'll have its conjugate. So that will be a buffer. Okay, so we didn't have to work that hard for this one because we were just directly adding something weak in its conjugate. Next up, we have some ammonia, NH3, and ammonium chloride. So the ammonium chloride, we know, is going to break apart in solution to form NH4+ and Cl-. So when we do that, we're going to have something weak, and we're going to have its conjugate added directly into solution, which means that we have a buffer. Okay, so again, we've just directly added the stuff. Now, looking at the next problem, we're adding a strong acid to a weak base. So, we're going to have a reaction between the acid and the base. We're going to have, it's a strong acid, so I'm just going to write H+, combining with NH3, and it will react completely to make NH4+. We have a reaction, so we're going to need our ICF table. Because we have our ICF table, we need moles. So I'm again going to do liters times molarity, which is moles over liters, to get out moles. Okay, and so then when I calculate the moles, I'll end up with 0.1 moles protons and 0.025 moles NH3. We're not starting with any of that. And so when we look at our reactants to figure out our limiting reagent, we're going to use up the one we have less of, which is the ammonia. We'll use that much of the protons. And we'll make that much of the ammonium. So what we're left with is a strong acid and a weak acid. So this is not going to be a buffer because we don't have any of the weak base to go with its conjugate. So 3 is out. For the last one, we're going to use the same kind of logic as we did before, because here we have a strong base reacting with a weak acid. So we'll have OH minus from our strong base reacting with the weak acid, completely reacting to form water and F minus. Because we have the reaction, we're going to have to do the ICF table again. So we'll need moles. And so for the hydroxide, we're going to have 0.1 moles. And for the HF, we're going to have 0.025 moles. Don't really care about water. Not starting with any of the fluoride. Okay, and so we're going to look at our reagents for the limiting reactant. In this case, it's going to be the HF, similar to the last one. So we'll have some of our strong base left, and we'll have made some of our conjugate base. So this is also not going to be a buffer because we're not left with HF and its conjugate. We only have the conjugate. Okay. That being said, you can make a buffer this way. It's just you need to end up, after the reaction, having some of the HF left over and then making some of the fluoride. Okay, so the answer here is just going to be D. And you have to do the ICE table or the ICF table when you have situations like 3 and 4. Okay, get ready, because here with number 15 we have a super long problem. We're trying to figure out the pH at the equivalence point of this titration, where we have a weak acid, benzoic acid, being titrated with a strong base. And so if we think about the titration curve for this, you can think about as we add in hydroxide, what will happen to the pH. So with our benzoic acid, we're going to start pretty low because it's an acid. And we're going to slowly, oh no, sorry, hold on. Okay, sorry, technical difficulties. So, as we add in hydroxide, we're going to start with a low pH, then it's going to increase in sort of that fashion. Let's see, make it a little more dramatic. So, we have kind of two regions of note. One is this kind of flat part where the pH isn't changing. And this region is our buffer region. And at its center is the pKa. And then the inflection point here is going to be our equivalence point. Okay, and so when you have a weak acid with a strong base, we know that our equivalence point pH is going to end up being above 7. The reason for this is that we're going to make some conjugate base as we go through our reaction, which will increase the pH. Another way you can try to remember it is to say we have a weak acid with a strong base, so the base is going to win out a little bit. Let's go ahead and look at this reaction here. We have our weak acid plus the hydroxide. The hydroxide is going to come in and take a proton from our weak acid and leave us with the conjugate base. Okay, and because this is a reaction, we're going to need our ICF table. And we know that for ICF tables, we always put in moles. So we're going to have to take the volume of benzoic acid and the concentration of benzoic acid to get to moles. And we're going to go ahead and take the liters times the molarity, which is moles per liter, to get out moles. And so that gives us 0.09 moles of our benzoic acid. And the definition of equivalence point is when the moles of our acid are equal to the moles of our base. And so here for hydroxide, we're also going to have 0.09 moles. Okay, and a step that's easy to forget but is important for these problems is to figure out how much of the hydroxide you'd have to add to get that many moles into solution. And for that, we're going to do the opposite of this calculation down in the bottom. Instead, we're going to take the moles and multiply that by 1 liter for every whatever molarity is going to give us the volume back out. So this is essentially going to be 1 over molarity. So I'm going to go ahead and say that I have 0.09 moles hydroxide, and from my concentration I can say that in 1 liter there are 0.9 moles of hydroxide. Meaning that I added 0.1 liters of the hydroxide to reach the equivalence point, which is 100 mils. So I'm going to go mark up at the top here that my total volume is equal to 300 mils. Okay, so now let's go through and fill out the rest of our ICF table. Don't care about water. They didn't tell us anything about the benzoate, so we have none of that to start. This is all in moles. Now when we look at our reagents to figure out what is limiting, we have equal amounts of both, so they're both going to be limiting. Both are going to get totally used up. Gone. And we'll make that much of this benzoate. Okay, cool. We're at the equivalence point. And now you can see that all we're left with is the benzoate. But we also know that benzoate is the conjugate base of a weak acid, which means that now we have a weak base in solution. So if we want to figure out the pH, we're going to have to go ahead and do an ice table for that weak base in solution with water. So this weak base is going to undergo a base hydrolysis reaction where it takes a proton from water. It's in equilibrium then with its conjugate acid. And hydroxide. And so now we have something weak in equilibrium. So we're going to use our old friend, the ICE table. So the thing with ICE tables is we put everything into molarity for those. We are dealing with concentrations for equilibrium. So we need to convert our benzoate moles into concentration, and that's why figuring out this total volume was important. Because now to get our benzoate concentration, we're going to take the moles from our ICF table and divide by our total volume, which is 0.3 liters. And then we can see that our concentration is going to be 0.3 molar. And we can bring that down into our ICE table. I'm going to disregard water. And we don't have any of these to begin. We used them all up from earlier. And then we're just going to do our old ice table stuff. Minus x, 0.3 minus x, plus x, x, plus x, x. Okay, and so we called this a base hydrolysis reaction. So what we're going to need is an equilibrium constant that's related to base, so Kb. The only issue is when we go up and look in our problem, the information that they gave us is the Ka for benzoic acid. So if we're going to convert between Ka for weak acid and Kb for its conjugate, we're going to have to use the equation where Kw equals Ka times Kb. We're at 25 degrees Celsius, so we can say Kw equals 1 times 10 to the negative 14. And we can divide by Ka. The 6.5 times 10 to the minus 5 to get Kb. And this ends up being 1.54 times 10 to the negative 10. And so that's what we're going to use when we set up our equilibrium expression down here. 1.54 times 10 to the negative 10. And we're going to take the equilibrium values for our aqueous products divided by the equilibrium for our aqueous reactants. We're going to solve for x. We have a k that's small enough, less than 10 to the minus 5, to allow us to ignore any x's that are added or subtracted, which makes the math a little easier. And we can solve for x, and we get that x is equal to 2.15 times 10 to the negative 5 molar. Okay, And then we have to remind ourselves that our X is giving us our hydroxide concentration. And to remember, we can look at our ice table. So when we go up here and take the negative log of that number, what we're really solving for is POH. And POH then is going to be 4.67. So our pH is going to be equal to, okay, sorry guys, let me go back a little bit because I made a calculator mistake. And it was just when I solved my K expression, I was doing it in Toggen and must have messed up. So let me just go back a little bit. Okay, not too far. So hopefully when you solve this KB expression, you'll do better. And you'll get that X is equal to 6.79 times 10 to the minus 6 molar. Okay. And maybe you caught me on that one too, because you were doing it as we were going. Okay, so just be careful when you're punching in your calculator. You get your X. It's still relating to the hydroxide concentration. And then we can go ahead and get the POH by taking the negative log of our hydroxide concentration. You get a POH of 5.17. pH then is going to be 14 minus 5.17, which is going to be 8.83. Okay, which corresponds to answer choice D. And that matches our prediction. We thought, hey, we have a weak acid, we add a strong base, so we know our pH should come out to be greater than 7 at the equivalence point, and that's what we found. Okay, so making these predictions beforehand can help you check the number that you get from your calculations. So it's always good to do that last minute check. And if you make that prediction beforehand, you can already rule out 3 of the answer choices, making this question then 50-50 instead of 20-80.